In 2024, a team at the University of Toronto fired photons through a cloud of ultra-cold rubidium atoms and measured how long the atoms stayed excited. The answer was negative, not zero, negative. The photons appeared to leave the atoms before they entered them. Light went backward through time, and then in 2025, a team in Vienna proved they could rewind a photon's quantum state with over 95% accuracy, without knowing anything about what happened to it. Everything you were taught about time, that it flows one direction, that causes come before effects, that the past is locked, might be wrong. And the proof isn't theoretical. It's sitting in a lab in Vienna, encoded in a single particle of light. Here's what they taught you. Light travels at 300 million meters per second. Always forward, cause comes first, effect comes second. You flip a switch, the bulb turns on. The photon leaves the filament, crosses the room, hits your retina. Past to future, simple, settled, done. But then quantum mechanics showed up and broke the rule. In the double slit experiment, a single photon passes through two slits simultaneously, acting like a wave, and creates an interference pattern. But the moment you watch which slit it goes through, the pattern vanishes. The photon acts like a particle. It's as if the photon knew you were looking. That was strange enough. But then physicist John Wheeler asked, what if you put the detector in Opry? After the photon has already passed through the slits, what if you make the choice to observe it after it's already decided whether to be a wave or a particle, the result? The photon changes its behavior retroactively. Your future decision appears to alter the photon's past. Wheeler himself said, a decision made on Earth today could in principle alter a photon's behavior from billions of years ago. In 2024, Daniela Angelo's team at the University of Toronto built an apparatus that took 3 years to design. They fired photons through ultra-cold atoms and measured the exact duration the atoms spent in their excited state. When certain photons, the ones that were absorbed and re-emitted, were isolated, the excitation time was negative. Not near zero, negative. The atoms returned to their ground state before the interaction should have been complete. The photon appeared to exit the cloud before it finished entering. Angelo described it this way. If you built a quantum clock to measure how much time atoms spend in the excited state, the clock hand would move backward. Not a metaphor, a measurement, peer-reviewed, published. And it forced physicists to ask a question that sounds insane. Can an effect come before its cause? Okay, pause. Before I show you the 2025 experiment that made this even more real, I need your prediction. Do you think negative time means A, time literally runs backward for individual photons, and causality is broken at the quantum level? Or B, it's a measurement artifact, and we're misinterpreting what the math is telling us? Drop a left arrow for time is broken. Drop a right arrow for it's just math. Lock it in. Theory A, the safe bet. Negative time is just a quirk of how we define group delay in optics. The photon isn't really going backward. We're measuring an average that includes quantum interference effects, and the average comes out negative. Like how the average number of children per family can be 2.3 even though no family has 0.3 of a child. The math is real. The backward time isn't. Theory B, the radical interpretation. Time at the quantum level is not a one-way street. Richard Feynman himself treated positrons as electrons traveling backward in time. The two-state vector formalism by Yakir Aharonov describes every quantum system using two wave functions, one from the past and one from the future, converging on the present. And the delayed choice experiments prove that future measurements can determine past behavior. What if time isn't an arrow? What if it's a conversation, and the future is already talking back? Then in 2025, Miguel Navasquez and Philip Walter at the Austrian Academy of Sciences and the University of Vienna did something that shouldn't be possible. They published a paper in Optica demonstrating universal quantum time reversal. They encoded a qubit into the polarization of a single photon, sent it through a Sagnac interferometer, and use the quantum switch to make the photon state rewind, return to exactly where it was before the experiment began, without knowing its starting state, without knowing what happened to it. Across 1,800 runs and 50 different evolution combinations, the fidelity was above 93%. Some runs hit 97%. Navasquez compared it to having a remote control for time, rewind to a previous scene, fast forward past several. And Walter added that this has immediate practical applications. A rewind protocol in quantum processors could reverse unwanted errors, essentially undoing mistakes by sending a quantum system backward through its own timeline. This isn't philosophy anymore. It's engineering. If time reversal works for one photon, the question becomes, where does it stop? Every particle of light in the universe obeys the same equations. Every photon from every star that's ever shown is, at the quantum level, time-symmetric. The arrow of time, the thing that separates your past from your future, that makes memories possible, that makes death irreversible, may be an illusion of scale, not a law, a habit, a statistical accident that emerges only when trillions of particles act together. At the level of a single photon, the future and the past are the same thing. So here's the question I keep coming back to. If a photon can travel backward through time, if a measurement you make today can determine what a particle did yesterday, then is the past really finished, or is it still being written? Tell me what you think. I genuinely want to know. If you want to go even deeper into the physics that's breaking reality, hit the subscribe link in my bio right now. Because next time we're covering Wheeler's cosmic delayed choice experiment, where a decision you make on Earth today can change what a photon did 4 billion years ago. I'll see you there.